Ever wonder how your phone predicts your next word? Or maybe how a medical system can suggest a diagnosis almost instantly? Well, it's not magic. It's just really cool probability. Today, we are diving deep into one of the fastest, most powerful algorithms out there, naive Bayes. We're going to go from the basic idea all the way to building 3 different models from scratch. So let's pull back the curtain and see exactly how this thing works. It really all boils down to this, doesn't it? Behind that instant sorting of your inbox is this brilliant piece of logic that's weighing evidence, kind of like a detective. This is the perfect real-world problem that naive Bayes was pretty much born to solve. And you know what? We're going to build our very own version today. All right, so here's our game plan. First, we'll get a handle on the Bayesian brain. That's the core logic. Then, we'll get our hands dirty and build a Gaussian model for a serious medical task. After that, we'll tackle text with 2 specialized classifiers. And finally, we'll put them all head-to-head in a model showdown. Okay, let's get right into the heart of it. We're about to demystify the formula that powers this entire algorithm. And don't worry, it's not going to be some scary math lecture. We're going to break it all down with a super simple analogy that, trust me, you use every single day without even realizing it. Now, I know this looks a little intimidating, but it's way simpler than it seems. Let's just stick with our spam filter example. The posterior is what we want to find. What's the probability an email is spam, given that we see the word free? To figure that out, we multiply the likelihood, how often free shows up in emails we already know are spam, by the prior, which is just the overall chance that any email is spam to begin with. See? It's just a formal way of updating what we think based on new evidence. So why the name naive? Well, it's because it makes this one big simplifying assumption, that every feature is completely independent of the others. In our spam filter, it assumes the word free has absolutely no relationship to the word win. Now, we know that's not totally true in the real world, but this little simplification is its superpower. It's a trade-off. We give up a tiny bit of nuance for a massive boost in speed. And honestly, the results are often still fantastic. Theory's great, but let's actually build something. We're going to start with Gaussian naive Bayes. This one is perfect for continuous numerical data, things with decimals like measurements. And we're going to apply it to a real-world medical data set to see if we can predict a diagnosis. Okay, first things first, we need some data. We're using pandas to get ourselves a nice data frame, and we're loading the breast cancer data set straight from Scikit-learn, which is super convenient. We load the features, we give them the right column names, we add our target variable, and then we just print the first few rows to see what we're dealing with. And boom, here's our output. You can see we've got all these continuous numbers, right? Mean radius, mean texture, all these measurements with decimals. This is exactly the kind of data where Gaussian naive Bayes really shines, because it's built on the assumption that these features follow a normal or, a Gaussian distribution, that classic bell curve. So before we jump into building, let's do a quick health check on our data. And yep, it's looking good. 569 patient records, 30 features for each one, and this is the important part, no missing values. This is a perfectly clean data set, and that means we can skip all the complicated pre-processing and get right to the fun part. All right, now for the magic. We split our data, holding back 20% so we can test our model on data it's never seen before. Then we import Gaussian NB, create an instance of it, and we train it with one single command. gnb.fit. That's it. Our model has just learned all the patterns from the training data. Then we immediately use it to make predictions on that unseen test data. And here we go, our first look at the results. Just looking at the first 5 predictions on our test set, they match the actual values perfectly. That's a really great sign that our simple model has already figured out how to distinguish between the 2 classes pretty effectively. Okay, so we've handled continuous numbers, but what about text? I mean, you can't exactly calculate a mean or standard deviation for a word like free. So for this, we need a whole different set of tools. Gaussian NB isn't going to work here, so we're bringing in its 2 cousins, Multinomial and Bernoulli naive Bayes. Each one has a really unique way of looking at words. Think of this slide as your cheat sheet. It lays out exactly when you should use each model. Gaussian is for your continuous numbers. You'll want to use multinomial when you care about how many times a word appears. Great for classifying long documents. And you'll use Bernoulli when you only care if a word is there or not, present or absent. Perfect for things like spam detection. So a machine can't actually read words. We have to translate them into its language, numbers. And that process is called vectorization. We're using Count Vectorizer to build a master list of every unique word it finds. We call that our vocabulary. Then, for the multinomial model, we count how many times each of those vocabulary words appears in every email. For Bernoulli, we make it even simpler. We just note a 1 or a 0. Is the word there or not? We do that just by setting binary equal to true. So after we do that vectorization, this is what the machine actually sees, a master vocabulary. It's a unique list of every single word from our sample emails. So from now on, an email like "win a free cruise" isn't text anymore. Nope, it's a vector of numbers, something like 00011000001, where each number just represents a word from our master list. And hey, just like with our Gaussian model, training these is incredibly easy. We just import multinomial NB and Bernoulli NB. We fit the multinomial model to our word count data, and we fit the Bernoulli model to our binary yes or no data. Just like that, 2 more digital brains trained and ready to go in seconds. So we've built 3 different models, but how good are they, really? Well, it's time for the showdown. We need to actually measure their performance with some hard numbers to see which one works best and maybe see where they're getting things wrong. This right here gives us a fantastic picture of our Gaussian model's performance. It's called a confusion matrix. The numbers on the diagonal, the 70 and the 40, those are our correct predictions. The ones off the diagonal are the errors. So we can see it correctly identified 70 benign cases, but it made 1 mistake, classifying 1 as malignant. And on the flip side, it caught 40 malignant cases but missed 3. This gives us so much more insight than just a simple accuracy score. So the final score for our Gaussian model is a pretty impressive 96.5% accuracy. I mean, for a model that's this fast, that's an incredible result. But what about our text classifiers? Well, the multinomial model, the one looking at word counts, got a stellar 98.2% accuracy on our spam data, and the Bernoulli model, just checking if words were there or not, was right on its heels at 97.8%. The showdown is over, and it's crystal clear. Picking the right naive Bayes for the job is absolutely key. So what's the big takeaway here? You should always consider naive Bayes as your first baseline model for a classification problem. It is blazing fast, it handles thousands of features without breaking a sweat, and as we just saw, it's an absolute beast when it comes to text. Just remember it's one kryptonite. If your features are super correlated, that naive assumption might just lead it astray. We've gone all the way from theory to code. We built and evaluated 3 powerful classifiers for both medical data and text, and we saw how each one shines in its own specific way. The logic is simple, the speed is just undeniable, and the accuracy is seriously impressive. So the only question left is, what problem are you going to solve with it first? Go on, get out there and start building.
Like and subscribe for SimplfyTech, explaining one concept at a time, simplifying the technology and AI.